Okay, I think everyone is here. So before we get started, I really briefly introduce myself. My name is stage1 from National Liang Jiao Tong University. Today, the second one is Professor Chen from National Central University. Professor Zhang from Shanghai. Professor Men from Zhongzheng University. Central University. So, each team, please introduce your team members, starting from reports.
My name is Andrew, the leader of the laboratory team. This is Danny, this is Bernie, this is Howard, and this is Hans. Thank you.
Okay, so I'm the captain for the team Relativity, and my name is Lin Yong Zhang. And as for my members, here is Chen Boyu, Wang Ruichen, Luo Dazhao, and Zheng Diyang.
Hello, we are Team Trivial from Jiayi Senior High School. I'm He Chengyou. It is Li Yi'an, Wu Jiazhen, Ye Jiayu, and Su Rongxuan. Thank you.
So we will get started in 1 minute.
Okay, so one in.
Okay, let's get started. And the opponent challenge the problem. 1 minute.
Okay, so we wanted to oppose problem number 16, Fusion capitals.
So the opponent accept or reject?
Accept.
Accept. Okay, good. And so the reporter has 5 minutes to prepare. Please write down the name on the blackboard. Okay, reporter, take the floor. You have 12 minutes.
Okay, good afternoon. I'm the reporter from Team The Grangers, and today I'm going to report problem number 16, cushion catapult. So this is our outline. This is the problem statement. So we have to place an object on a large air cushion and drop several other objects in such a way that the first object is catapulted away. So we have to investigate how the exit velocity depends on relevant parameters. And so we pointed out two main focuses. So the first one is how do relevant parameters affect the exit velocity, and second is what are the conditions under which the exit velocity reaches its maximum. So this is our observation video. So this is our model simulation. Okay, so this is the definition. M1 is the mass of the first object, which is the one that was hanged by the string, the release one, and then M2 is the mass of the second object, which is the object being catapulted away, and H1 is the release height, and H2 is the maximum height of M2. And so these are the discussion of perimeters. We did 4 experiments. So there are 4 independent variables. The first one, we are discussing the mass ratio of the 2 objects. The second experiment, we are going to discuss the release height. Third experiment, we are going to discuss the cushion height. And the fourth, we're going to discuss the distance between 2 objects. So these are the dependent variables: the contact point, angle of impact, mass of M1, and release height, mass ratio, distance between 2 objects, and cushion height. Okay, so this is our methodology of doing the experiment. So experiment setup. What we have over here is a pulley system over here, and then this is just a schematic diagram of our experimental setup. And then we have a string hanging the ball over here, and then so this one is the releasing object, and we also placed a washer as the N2 to be catapulted away. So this is basically our experimental setup. So how do we measure? We define the unit length. So two black lines are 5 cm apart from each other. So I don't know if it's clear enough, but this is 5 cm. And then where black and red lines are 2.5 cm apart. And then we mark the initial position and the maximum height to measure the distance traveled. So we mark it over here and then like see its placement, and then we can measure the velocity. And elasticity, so we altered the volume of the air cushion by adjusting the height between the table and a plastic board, which was placed on top of the air cushion. So this is where what we will do in the third experiment. We are changing the height or the thickness of the cushion. So this is the diagram of our perimeters. You can see over here the release height. This is experiment 2, and distance between two objects, which is experiment 4. Mass ratio between these two, first experiment, and then the height. So these are our experiment data. Experiment 1, mass ratio versus initial velocity. So you can see over here the tendency. We can see the slope of our experiment and our model are nearly like the same, but we can still see a significant difference between them. But what we can know is that it's because of this chart. The energy lost is really significant, like it's almost like 90% in each experiment, and I'll explain it later why the energy loss is so significant. And this is our second experiment talking about release height. And then, so this is also a comparison between our experimental data and our model. And then we can see like the trend is also still the same. It's like a perfect like linear relation. But then we can also see like the velocity, the difference is like really huge. And that is also because of the energy lost in all of these experiments. So experiment 3, the amount of air in cushion, so versus our initial velocity. Okay, so this is the result. And we can see like over here, 8, it reaches the maximum initial velocity when the height of cushion is 6, and then we can see it is like a curve over here. So this is also the analyze for the energy loss. And the fourth experiment, we are discussing about the distance between two objects. And this is what we did, the result. And so we can also see the results over here. When two objects are like really near to each other, the initial velocity would be pretty small. And then so does if the distance is really like huge. So you can see optimal distance between the two objects, which is over here, 20 cm. And also the energy loss result. So this is our theoretical approach. So the height of the first object. So through our experiments, we noticed that varying the drop height led to distinct initial velocities. And then there are some comparisons of the videos. So you can see the height that it reached. And then the second video, when the ball is way higher, you can see the washer. The catapulted height was way more bigger than the first one. So, and we can see, and this one is talking about the mass ratio between two objects. So during our experiments, we noted that altering the mass ratio led to varying initial velocities. to substantiate our claim, we applied the work energy principle. Yes, so you can see like the different mass ratio. And then so the work energy principle is shown like this. This is the formula. And then the confirmation of the conservation of energy validates both the mass ratio and height, play crucial roles in influencing the initial velocity. And the next we are talking about distance between two objects. And then in our preliminary observations, we additionally found that the separation distance between two objects may play a role like the same. It is also a factor that impacts. And then so when the cushion undergoes compression, the energy is transmitted via a compression wave. And then if the objects are too close, the wave might disperse excessively. And while they're too far apart, the wave might have like dissipated too much energy. So it doesn't bounce. No, it doesn't get catapulted away. So you can see if it's too near, the washer still stays there and doesn't really catapult it away. And then you can see this. Okay, so another point we're going to discuss is the elasticity, and variations in the Cushon's elasticity lead to alterations in the coefficient of restitution. And then it causes differences in energy transfer efficiency. So this is our data analysis. So this is the first experiment, the mass ratio and initial velocity chart. And then we can see when mass ratio increases, the exit velocity also increases. Second experiment, we can see the slope of the tread line is 0.19, and this is a chart of release height and initial velocity. So what we can also get is that for every centimeter increase in the ball's release height, the exit velocity increases by 0.19. And this is our third experiment, and then we can see at a height of 8 cm, it resulted in the lowest energy loss. Fourth experiment, we can see a trend because it is not really like a linear chart or something. So I can see like the exit velocity shows an increasing trend with the distance between the two objects to a certain point, which is over here, approximately 20 centimeters, and then starts to decrease again. So there should be an optimal range for maximizing the energy transfer efficiency. And then these are our conclusions. So the maximum velocity reached at 40 cm with a setup distance of 20 cm is 4.164. This is just our experiment data. And then the optimal setup still has an energy loss of 93.5%. So that is a significant problem that we need to solve in the future. So what causes the energy transfer efficiency to be so low? Because we cannot predict like the air or the flow inside of the cushion. So maybe I listed out 3 reasons: the internal friction in the cushion, air resistance not considered, or maybe the M1 energy didn't fully transfer to the cushion. Maybe it transferred to the table or something. So that's what makes the efficiency so low. And this is our normalized velocities. We put it into normalization, and then we can see these 4 factors. Release height affects the most, and then the mass ratio affects the least. So this is the end of my presentation.
Very good. And the opponent 2 minutes to ask questions.
Okay, so here the first question is, can you bring the page of your experiment setup? Yes. So how do you control the string of the angle to be vertical to the cushion?
Oh, so we wait until that it is vertical. So we don't release it when it is still shaking.
Okay, and then the next question will be like, how do you consider that if you use the string for the ball falling, do you consider that it's a free falling regime, or it will be affected to the surface tension of the string? Do you consider that?
do you mean like? I think our assumption is it is a free fall, but can you explain like
I
where
think that how
will
do
they?
how do you make sure that in this condition experience procedure it is all because of it is all in the free falling region? Do you have any assumptions or improvement to make sure this condition?
I mean, this is my assumption. So the maybe surface tension or something that you just mentioned is not in my consideration.
I mean the tension of the
String. This one?
Yes.
Oh, we didn't consider it.
Okay, so can you turn the page of the problem statement? Yes. So how do you define the large cushion?
Large?
Yes, in the problem statement, it has mentioned you use a large cushion. So can you define what is a large cushion?
So it doesn't define a large cushion, but if you have a small cushion, there should be a boundary for bouncing. If you have a cushion that is as big as the ball, the releasing ball, I think that it might not
Okay,
have any.
so you may consider this because of the mass rate of the cushion. The falling radial reverse to the falling of the
Okay, time's up.
Sorry.
And opponent has 3 minutes to prepare. Okay, opponent, you can take the floor.
Okay, so good afternoon, fellow listeners and honorable judges. I'm the opponent from Team Relativity, and today I'm going to oppose problem number 16, cushion catapult. And here will be the problem statement. If you place an object in a large air cushion and drop several other objects in such a way that the first object will be catapulted away. So you have to investigate the exit velocity depends on relevant parameters. And for this discussion, from the problem statement we have mentioned, they have several identical objects. But from the reporter's report, we didn't see that, so next will be the discussion of how it will affect this phenomenon. And as for the theory part, they have used the energy transform rate, energy loss, and the maximum velocity of the object to concern the experiment procedure in this problem statement. And as for the experiment, they have used the parameters such as the ratio of the mass, the placement of items, the drop heights, the cushion type, and the cushion volume. And for the setup, they just used a cushion and item dropper, which connected with the three following region that has been mentioned. And as the reporter, we considered that it has a strength of complete qualitative phenomenon explanation on how they concern this experiment procedure by using the method on how they have a qualitative explanation. And also they have a lot of experiment to prove and the assumption of how the energy loss trend will go on. And also have a qualitative understanding and conceptual clarification. But as for the suggestion, we considered that they have a lack explanation for the experiment results, since that, as firstly, is that the energy loss part, we didn't understand that why the energy loss will be so high, up to 93.5%, and we think that is too high, so that will be a discussion further that from the discussion part. And for also is the analysis method that they didn't have mentioned how they have to measure the exit velocity from the experiment. And also in the conclusion they just mentioned that how they shoot, but we didn't make sure if it is vertical shooting out or in a projectile motion. And so thirdly, they have no max theory or model to discuss the physics principle during how the ball has put in the cushion, how the ball has an impulse on the cushion and make the ball has the exit velocity. So in this, in all the report presentation, we didn't see some physics principle in the explanation of why this phenomenon would happen. Okay, right?
Okay, then we can proceed to discussion.
So what? So for the discussion, firstly we have to discuss about the simple physics explanation about how does the energy transfer in the cushion and why the loose energy is so big, so up to 95%, because we think that it's not really reasonable. So that may be a discussion first. And secondly will be the quantitative modeling of why the theory line doesn't fix the experiment data and the definition of large cushion. And thirdly is the conceptual clarification of what is the physics meaning of alpha that they have mentioned is the energy transformation coefficient and of the explanation of the trick. And lastly, we'll be discussing about the principle how the cushion is as the ball drop to the cushion, the impulse and because we consider that will be the membrane and the aerodynamic part, which two characteristics will affect this. We have to discuss about which is the most important parameters which factor to affect this phenomenon. And next will be the discussion. Okay. So firstly, that you have previously mentioned is that the define of large cushion, right?
Yeah.
So next question is from this experiment setup, how do you make sure that every time the cushion will be stable in this place?
Oh, so we stick the cushion onto this board, and then we also stick. We actually like stick it over, and then we don't change the placement or something. All we do, the parameters that we change are on top of the cushion. So we didn't do other. Like we didn't change it.
So what's your method for making the cushion at the same place every time? Just really stick there?
Yes, stick it.
Okay, I understand. So can you finish page 12? Yes. At this part, you have mentioned the elasticity of the cushion, right? So in my considerations that the cushion have two characteristics or factor is as for you have pumped the air into the cushion, they have firstly is the membrane up to the cushion, which as the ball hit on the cushion, there we have some kind of a membrane if you pump too much air inside. Like the aerodynamic part might not be the main factor. But secondly is that if you don't pump that much of air, that maybe there will be the aerodynamic part as considered as a lever system. So which factor do you think is the most important to consider these two factors, and can you tell me the most optimal condition? And yes.
Just like you said, this links with our third experiment amount of air in the cushion.
Yes.
So we can see over here, when the height of cushion is 4 cm, it kind of like, it just means that there isn't a lot of air inside of it. So that kind of matches like the second kind of situation that you just described. And then when we pump the air and make the cushion is 12 centimeters high, then it quite matches when the first situation that you mentioned, that when we pump too much air in it, and then the cushion is no longer like maybe it will like turn to solid or something. So it's not like if you pump too much air into it, it kind of becomes like a solid.
Okay, I understand. So what you have mentioned is that at this part, it's more considered like a lever system due to the aerodynamic part, right? And at this part, it will be considered as a rigid project, right? So how do you consider that? How do you have any physics modeling to explain this phenomenon because that's the ball falling to the cushion, it has an impulse, right? So do you consider this impulse?
We like this is our experimental result, and then we can see over here like 12, the energy lost is more than when we put it at 8, so that is why the velocity is slower also. So I mean, like, you want me to have we don't have a physical theory or model that matches all of the factors that you mentioned.
Okay, I understand. So as I mentioned, I understand that the theory modeling will be a part of procedure, but as for the equation you have used is for the work, right?
Yes.
But I consider that the impulse condition may be a more fitting modeling because that it has, as the ball falling to the cushion, it really have an impulse and it is connected to the contact of how the ball has been in the cushion. So how do you consider that the contact time of how the ball hit the cushion will affect this phenomenon?
We used we have like observation videos, and then we have measured it. Yes.
So are there certain conditions that impulse is very small or very big? Are there some boundary conditions?
Can you like specifically say what's impulse? Like what are you trying to say?
I mean that. It is normally if it's a cushion like this,
yes.
right? So normally the ball will have a free falling region to fall to here. So normally if there's an impulse, they will cause something that you mentioned is they will have energy transfer to the cushion, and as for making the ball to exit like this, right?
Yes.
So my mean is the contact time of the angle.
I think the contact, you want me to explain about the contact time now or the catapulted away angle?
Sure, I mean an impulse is because that is the definition of the every force which in every second of time about how the ball hit the cushion. So which means that the contact time will be an important factor to this phenomenon. So I consider it will be a good discussion for the experiment to adjust for some suggestion for your theoretical model.
I guess it's hard to measure, so we focus on the catapulted away object. We didn't we didn't apply this formula to
Okay.
here.
I understand what the reporter mentioned, but the reason why I consider it is because of impulse, because that in the problem statement it had mentioned that there's several objects which falling in the same cushion to make the exit velocity, right?
Yeah.
So which means that in certain conditions, maybe if I add 3 objects falling at the same time, it'll have have the same mass of m. So it has the 3m mass falling in a certain contact time. But however, in other conditions, if the 3 ball falling in different time, the impulse of time will be different. And also the mass will be different. So I consider that it will be an important parameter for this problem statement to investigate more deeply for this problem statement and for the model. I understand. Okay. So then how do you? Next question will be that if the ball is here, so how do you? The method of you measure the exit velocity is the direction of this point, or it's just the vertical axis.
So we did some experiments before, and then we can see. So it is actually related to what my experiment over. Where is that? Or yes, this one. So I can see at 20 when the initial velocity, the exit velocity is the largest. It also is the placement that the second object will be catapulted away vertically. And then, so after 20, when the distance is bigger than 20, then it starts to have a tilt angle when it is catapulted away. And then when it's smaller than 20, then it has the opposite angle of catapulted. But yes, I think we applied different formulas to this to the measurement of this exit velocity.
Okay,
So I don't think you need to be worried about that.
So, and I understand your meaning as because of the surface of the pebble is such as a curved membrane.
Yeah.
So as for the distance between the ball will cause different distance between the two ball will cause different angle of the exit velocity.
Yes.
Okay, understand. So then, can you tell me why the modeling of this part is not so fitting to the experiment? Are there any deviations discussed or some error to correct? Which means that from your model, the exit velocity will mainly be like about 15 to 20. But from your theoretical model, is it about the energy loss or?
Yes, that's because we cannot analyze like how the air inside of the cushion kind of works, and then so there are a lot of energy loss, and then even if we look at this, over here, the height of the cushion when it's 4 centimeters, you can see the energy loss is 99.8%, and then I guess it's because when the cushion is only 4 centimeters high, it kind of hits the ground. So it is not, the energy of it is not completely transformed to what can make the second object catapulted.
Okay, so you consider that it's because of some maximum and minimum conditions of cause this phenomenon.
Yes, I mean, you cannot have like too thin cushions, but you can't also have like too thick ones.
Okay, understand. I understand what the reporter wants to mention. So it's because of the thickness of the cushion, right?
Yes.
So do you consider that in every cushion, the air pressure is same or different?
Also, we use the.
So I mean, it's like how many air you pump inside will the air pressure change?
We didn't. We used to measure the pressure inside of it using the software in the cell phone called Firefox, and then but we use it. We replace it instead of we change it to.
Okay, time is
using,
up.
Oh, sorry.
Opponent has 1 minute to summarize discussion.
Okay. So first we have discussed about the problem statement of how the energy transfer in this condition, and secondly we have discussed about some physics modeling about firstly the membrane and secondly the aerodynamic part, which is the two main factors for this problem statement. And secondly, we have discussed about how the contact time will affect, because normally if there are several items falling at the same time, the time between each object has falling will cause different impact and will have different impulse. And thirdly is that the direction of the ball after it exits will be important, and we consider for the discussion is mainly because of the membrane is a curvature system, and between different distance of the two balls will affect the direction of how the ball has been exited. And lastly, we have mainly discussed about how the air pressure will affect this phenomenon. And as for my considerations, if the cushion is not fully full of air pump, all the air pressure will maintain the same because of the PV and RT.
The reviewer has asked a question.
So the first one is, I would like to ask the opponent. So you want the reporter to give a qualitative description, right? So what is your qualitative description?
I consider to use impulse to describe about the energy transfer coefficient. Yes.
Okay, so it's the impulse.
Yes.
Okay, and I think you said you don't have a quantitative description, right?
Yes, I don't have a formula to like integrate all
Okay,
of it.
okay. So the second is the problem statement says that you have to drop several other objects. So did you drop one object or multiple objects?
The ones I presented up there
Yes.
are only single.
Only single objects. Okay. So but the other thing is the problem statement mentioned the first object. How do you define the first object?
What do you mean?
The problem statement says that the first object is catapulted away.
Yes.
How do you define the first object? The first object. Yeah, what do you think? How do you define the first object?
I mentioned here is because that normally, as we have mentioned, the distance between the ball and different.
So
Like, can I answer? Yes. I only put one washer over there.
Only one
so-
object. Right, one object.
Yeah.
But what do you think?
I consider that from the reporter's problem, he used only one object.
Okay. So if we place multiple objects, what is the first object?
I consider it's because the distance of the impulse ball and the first object.
Oh, so it's the most closest one.
Yes.
Okay. So the second is the problem statement wants us to analyze the velocity, right?
Yes.
So do you think we should analyze the speed, the angle, both, or none?
Yes, I
Speed
considered both of them.
Both of them. So
Yeah.
did you place the like direction of velocity in your report?
The direction.
Yes.
No, I didn't place it. I didn't place the velocity of it.
Okay. What do you think?
I consider it as because different angle will have different exit velocity.
Yes.
So I consider that angle will not be the most important part because if you put the ball in the different place of the cushions, that the exit velocity will be different in
Yes.
its position.
So you think only the speed is important, the
Yes.
direction is not important?
Yes.
Okay. So second thing, you said you use the work energy theory, right?
Yes.
But you said there is energy loss.
Yes, I used the energy loss. Like I have a mass over there, and then I have a height over there.
Yes.
I have a mass of the washer, and
Yes.
then I have the catapulted height of the washer, and then so these two should match. But if they don't match, the rest are the energy loss. So that's how.
So do you think he can use the work energy theory?
I consider that the work energy theory is a rough explanation of this problem statement and it somehow has some fitting to this result. But I think the most optimal is the impulse because it's nearly the same explanation but has considered
Okay,
the concept.
time's up.
Thank you.
Reviewers, 3 minutes. 2 minutes. Okay, reviewer takes the floor.
Okay, honorable judges and fellow debaters, I am the reviewer of problem 16, question catapult. So the problem statement is as follows, and I want to emphasize some points. First, he said there are several other objects, and as the opponent noted, it needs a large cushion, but I don't think this is the point of the problem. And also, it mentioned that first object, and also the exit velocity. So I think these are the main points. So for an overview of the report, the reporter used a model simulation. However, they did not present any physical formulas. And also, they mentioned the pressure wave, and also they used the work energy theorem. And for the experiment, they used a pulley to control some initial conditions. And they also made a plot of various parameters, for example, the height and initial velocity. And they also discussed a lot of variables. So a few remarks to the reporter. They used a model simulation, which is their theory, and they analyzed the energy loss and a lot of parameters. However, some suggestions is that they should have a qualitative description, just like the opponent who said the input is the most important. And they should present some physical equations. For example, they mentioned the pressure wave. So they should introduce the theory wave equations. And for the experiments, they should add a bar. And for some other things of the experiment, we can see the ball swinging in their video. So it makes us doubt whether the experiment is well controlled or not. And also, just like the opponent said, they should have simple physical descriptions of the phenomenon. So to the opponent, they have noticed the problem statement could be discussed. So they discussed the large cushion. And they mentioned a simple physics model should be made. And also they discussed two very important things, that is the contact time and the direction of exit velocity. And for a few suggestions, he said that I think that they shouldn't focus on the large cushion part because the opponent also didn't give their definition of large cushion, and they should provide a qualitative description first because that's the most important. So for the discussion, lastly, the last question I asked is the work energy theorem. So the reporter thinks that it's okay to use, but the opponent thinks it's not okay because there's energy loss. And our idea is that he shouldn't use energy loss, and he shouldn't use the work energy theorem because there is a significant energy loss. And for the other problems, I discussed the importance of the speed and direction of velocity. So I think these two things should both be discussed because velocity is a vector, so it has a speed and a direction. So I disagree with the opponent that he says the direction doesn't matter because we want to analyze the velocity. And the reporter thinks both are important, but they can add the direction into their report. So for the second thing, if we go back to the problem statement, you can see that they want to drop several other objects. So the reporter didn't complete this part. And the opponent did discuss the case of multiple objects, where they discussed 3 objects. So I think that's a good part. And also, there is, so also we discussed the definition of the first object. So by the problem mentioning there is a first object, there should be multiple objects on the cushion. And the reporter only did one object. So I think they can do more objects, and that is a part that they can improve in the future. And that's the end of my review. Thank you.
Okay. So the report was summarized.
Okay, so I'm going to do my concluding remark. So this is a summary of my report. So I have analysis of several variables: drop height, placement, and the thickness of the and mass ratio. And then I talked about energy loss, maybe wave dissipated or elasticity. And I also mentioned the optimal distance for maximum energy conservation, but though it still has 93.5% energy loss, so that is the part that I have to work on. And then this is the normalization of parameters, which tells me which parameter affects the most, which is like the least important factor for this experiment. Then the opponent, he clarified an explanation of a trend, and then definition of a large cushion, and the first object is the closest according to his response. And then he talks about qualitative description, and then also pointed out the problem that ball swings, and also mentions the problem of impulse. And this is our discussion summary. how to make sure the cushion doesn't move, I stick it on the board. And then the elasticity of the cushion. So I change it. So when the air is little and when air is too much, there will be different elasticities to the cushion. And then he also mentioned about impulse, but we know that contact time is too hard to measure. So then we turn to use work and energy principle to analyze it. And then he also said about curved membrane, and then it correlates with the experimental results. And I think that is great.
Okay. Question from Yuri.
Why do you think the problem states that dropping several objects on a cushion? Several. Why does it want to drop several objects on a cushion? The reporter uses just one, right? Why
Yeah.
several?
Yes. You mean why?
Why the problem states dropping several objects?
I think it's because the problem statement wants me to investigate how the second or the third releasing object will affect the catapulting object when the first is.
The first object already left when you drop the second. My understanding is the problem wants you to find out when you drop the second object, the third object, what happened to the first object separately. The comparison. That's my understanding.
What do you mean first and second object?
The first object, when you drop the second object, first object leaves.
Yes, yes.
And you put back the first object, and then you drop the third object, first object leaves. Left. And then you compare.
So I have a second.
Not consecutively.
Yeah.
Dropping it, because the first object already left.
Yeah. But
There's no meaning to drop
Yeah.
the third object. So,
yes.
wow. How do you guys think?
I consider that the first object in this definition is the ball which has the x velocity, and as for the second, third, and fourth object is the ball that is falling through another side of the cushion. And for
It has nothing to do with the first object anymore, right?
yes, and I consider
Then why?
it has because it's the second, third, and fourth object. If they have the same time for falling, then the impulse will be different as for the second, third object falling in different time, which cause different impulse and making different exit velocity. Like because the impulse is related to the contact time.
So you mean you repeat the experiment several times?
No, I mean it's at the same condition as firstly, here's a cushion like this, and the first object is here. And firstly, I just dropped the second object at about smaller than one, just like the most qualitative experiment is like you just use 3 balls in different heights. Then you can see it to just hit, and have different contact time, which cause different impulse.
Yeah, so I think as the professor said, if the objects are dropped at different times, then there's no meaning of the third and fourth object. So I think the problem statement implies that we have to drop them at the same time, because if we don't do that, there's no meaning of future objects. So I think the meaning why the problem statement wants us to drop multiple at the same time is because their impulses may add. And if we think about pressure waves, it's like they may form a constructive interference or destructive. So maybe sometimes they add, sometimes they cancel. So I think that's what the problem statement actually wants.
Can I answer it again? Like, because I didn't understand what you were talking about at the first. So you mean when I have first releasing and then the second bounce and then I have the third one and the second one bounces? Is that what you mean?
No. That's
So-
what the problem is.
Okay, any other questions?
So both opponent and reviewer emphasized large cushions in the statement. So I want to ask all of you that what's the point to use large cushion? So from the reporter.
If the cushion is not big enough, it is not able to recreate the phenomenon.
As I consider, it's the relative between the volume of the ball or the volume of the cushion, they have a mass radial relative. So if the ball is small, the large cushion may be smaller in this condition. But if the ball is very big, the cushion might be very big to have the condition of the factor of the membrane condition and the aerodynamic condition that we have previously mentioned from the discussion.
Yeah, so however, if the cushion is too small, the top surface may bend like this. So first, it's not able for you to put balls on top. And second, it's hard to control the environment conditions. But if the cushion is large, then maybe near the center, the surface is flat. So we can control the experiment better.
Question? No.
Oh, but now I'll ask a quick question. Question for the reporter. I think you're gonna agree with me that the physical property of the cushion must change with various air in the cushion, right? I mean, really the height of the cushion.
Yeah.
So with that, why your data shows that the initial velocity is independent of the releasing height as well as the cushion height? Why it's so flat? They are independent.
Can you say it again?
The question was, the physical property of the cushion changed was various height of the cushion, right? But your data shows that your theory shows that the initial velocity stay flat, meaning that it's independent of the releasing height and the cushion height.
I think it's maybe the mispresentation of my report. I typed it wrong or something.
No, your data shows flat.
Oh.
That's fine.
Okay. Please be seated. So we now give the score for the reporter. Eight, 6, 5, 7, 5. For opponent, 9, 8, 7, 8, 7. For the reviewer, 9, 9, 5, 7, 7. Okay. Also, we conclude this.